Swayam Prabha. Digital India. Educated India.
So here is how you would sort of lay out the numerical solution for PDEs. Okay. So in general, it's not possible to find an analytical solution for a partial differential equation. Here I'm slightly generalizing. I've used this one-dimensional understanding or whatever little understanding we have obtained to now say statements more generally. Okay, this is a general philosophy or general whatever I'm ruminating on it or whatever. So I'm saying things more generally. Okay. So you would therefore want to try and solve such a problem through what are called as numerical methods. You can't solve this analytically, so you try and determine if there are ways to solving it approximately and therefore numerically. So in order to do this, we would have to replace by smooth, you think of it as these functions, like my right-hand side function is some complicated, whatever, exponential tan something with the arguments being weird. I could try and replace it by a polynomial approximation and try and integrate that. Okay, so I could replace it by discrete doesn't necessarily only mean point samplings. In this case, it could also mean by polynomial approximations or approximations by simpler functions that I can integrate if it is possible. Okay, so the whole idea is to then be able to compute this solution either with an approximation analytically or maybe pointwise. We'll get to the pointwise thing next. Okay, so we can approximate the PDE itself. So it turns out in this broader setting, you can do two things, one of two things, more or less. There may be other things as well, but one of two big things that people do is you either discretize the operator itself. So I might use a simpler operator for whatever reasons. It might be easier to then solve the approximate problem with a simpler operator, or you approximate the unknown solution because I might not be able to express it analytically. I might use some simpler approximations for it. Roughly speaking, the first method, which is where I discretize the operator, yields a finite difference like method. That's what it does. There's a side note here, which is about finite volume, but if you have never heard of it, don't bother. Okay, and then discretizing the solution yields what's called as the finite element method. Okay, technically it's not the solution that we are discretizing. We are discretizing the solution space. Okay, the space of L2 functions which are twice differentiable. That's what I mean. Okay. So both these methods can give you very high order or highly accurate solutions. What that means is in some limit, as some limiting process becomes infinity or something goes to zero, in some limit, these solutions, even if there is no analytical solution that you can write down, these approximate solutions can be shown to converge to the true solution, even if you can't write down a true solution. Okay. But since we are dealing with shape modeling, it turns out you rarely need to go beyond the lowest order methods in graphics, because if my solution is 20 digits accurate or 2 digits accurate, the way if I plot it and visualize it, it's not going to make much of a difference visually to me. And in any case, data is not going to be accurate. And so often you just are happy and you can deal with things in the lowest order methods. And that itself gives you enough fodder for doing applications. Okay. And also there is this trade-off with cost versus accuracy. One thing is you might not care if the solution is 20 digits accurate, but the other thing is to get the 20 digits of accuracy, you might have to expend a lot of computational power, which is probably not worth it in a real-time gaming engine or whatever your graphics application might be. Okay, and in any case, most GPUs, as I understand them, do only like floating point computations. So essentially, lowest order methods is what we care about. So let's understand these lowest order finite differences and a little bit of finite elements as well. But let's understand this and see how we can use this to solve the Laplacian problem, the Poisson problem. in 1D to begin with. Okay. Okay, let me pause and see if there are any quick thoughts, comments, questions. Okay, if not,
What is meant by leads the same method?
yeah, there are certain things like this I wrote. We will revisit this towards the end. If you stick around, if you're not tired and bored, you will see a little bit of what I mean when it yields the same method. Yeah, that's a good observation. It's innocuously written there, but yes, there is something about these finite difference and finite element lowest order methods that they coincide. Okay, so I already talked about it. So we'll understand the finite difference discretization of Laplacian in 0, 1 on R. That's not R. Okay, so what do we do here? So the basic idea in a numerical method for a differential operator, let's say d square by dx square, is that you can think of the derivative as being expressed by tangent lines in 1D for functions. And what we are doing is we are approximating the tangent by some secant lines. So this is an illustration figure of the derivative is the tangent. Maybe I can't compute it directly. Let me approximate it by a secant for some relatively reasonable neighborhood points. Okay. So in our case, the problem domain is still 0, 1. So we'll try and see how we can choose discretization points. Usually you choose discretization points by specifying a step size, and you sort of just linearly discretize 0 to 1, for instance, maybe. Okay, so this is a typical discretization. There's no requirement for it to be uniform like I've shown, but we'll just play with, again, simplicity for the sake of understanding. Okay, so this is a discretization of 0, 1, and this is a typical interior point xj and its neighbor xj minus 1 and xj plus 1. That's a typo. Okay. Okay, and I have a little bit of a note that this delta is not the Laplacian, so be careful. This is just saying delta x is the distance between any two successive points. Okay, I could have called it a little delta of x, but notation is somewhat standard, and we'll leave it as delta of x. Okay, so what do I do with this discrete points on 0, 1? I can approximate the tangent by a secant like the following. So I have xj, that's the point at which, sorry, I want to compute the derivative. I take the secant line between xj minus 1 and xj plus 1. Okay, this is the high school version of secant lines and so on. Yeah, this is basic geometry. Okay. Okay, so the xj's in the setting are called as grid points, and just showed you a typical point and its neighbors, right? Okay, now I want to tell you what is this notion of a difference quotient. Okay, so I think of a function whose derivative I can take. So recall from earlier in this presentation, C1 means the function is in L2. You can take its derivative, and its derivative is also in L2, and this is on the domain 0, 1. Okay, so we want to now consider how to approximate the derivative of u at a point using this so-called difference quotient. This is again, pardon me if you find this somewhat basic, but this is how you would do it. So I can use, there are three different ways. I can take, this is how you might define the derivative in like class 11 calculus itself, that you take some neighbor, you take a small interval around the point and then let this limit go to 0. In the limit delta x goes to 0, this will be the derivative if that limit exists. Okay. Okay, so but here are three different approximations for this derivative. In the first, I pick xj plus 1 and take the difference between xj plus 1 and xj and divide by the delta x. Or I can take xj and xj minus 1 and take the delta x. Or I can take xj plus 1 and xj minus 1. This is kind of the secant idea. And divide by the distance between xj plus 1 and xj minus 1, which is 2 delta x. Okay. So there are some implementation. If you're going to try and implement this on a computer, you need to be careful that this left quotient is not defined for the first point. So you'll have to remember this. I should have put this in the next slide also, but my bad. So you'll have to remember this. Because there is nothing to the left of this, I can't compute this at x equal to 0. And likewise, I can't compute this at x equal to, sorry, this middle one at x equal to 1 because there's nothing to the right of it. Okay.
Is it like then we cannot apply, use the boundary conditions fully if we use any of the first and second?
In fact, for those boundary points, you'll end up using the boundary conditions because you're given some information about those points. Yeah.
I can get you. Like,
so okay, so this one you can't apply this one on the left-hand side boundary,
okay,
right? But I'm anyways given right now. Remember, our model problem is Dirichlet boundary value problem. So I'm already given some value at this point, so I'll just use it. I don't have to use this derivative approximation.
Okay, so you will just skip it and go to the next one.
Yes, I'll start from x equal to 1. And even though I can compute it at xn, I will not do it because I'm given this boundary value.
Okay. So
Yep.
why won't you equal it to that boundary value? As in, why won't
Yeah,
you
I will equal it. I will not compute the derivative, right? Because my boundary condition is u of 1 equals some 0, or in this case 0.
Okay.
Does that make sense? So it'll show up.
Okay, I'll wait. Okay.
Yeah. Okay, so it's going to show up very soon. Yeah. Okay, so we'll denote these unknown solution at the grid points as uppercase uj. Okay, so u of xj is uj, and these have some standard names. This is called as the forward difference quotient or the forward difference formula. This is called as the backward difference formula, and this is the central difference formula. Okay, and using this new terminology, I'm going to introduce notation. I'll say the forward difference is represented by partial x plus, partial x minus, partial x hat, and I'm just rewriting it. Notice, so in this, I'm going to replace u of xj by uj and so on, and introduce for u of x, this primes, this new notation. Okay, that's all I'm doing. So this is what I get. So essentially, it's saying how the values between two successive points are used to compute the derivative at that point, or values in the neighborhood are used for computing the derivative at a point. Okay. So I'll come to it, but we have something defined, and I claim these are approximations to the derivative. Let me once, since this is also sort of like I'm kind of a mathematician, or at least pretend to be one, I'll need to show you some backing up of my claims. Okay, so if I were to claim that these are approximations, I'll have to give you some proof that indeed these are approximations. So let's do this only for this one particular case. Won't do it again. So let's show that these derivative approximations in the previous slide are indeed approximations, and we are going to use Taylor series, nothing fancy. And I'm going to assume all of you know Taylor series. You can always open Wikipedia on the side in your browsing window and look at it in case if you've forgotten, but hopefully not. Okay, and I'm going to use the so-called Taylor series with the remainder form. Again, this is if you're not feeling like it, you can skip this part without worry. It's just for sort of some completeness in my mind. Okay, so we need to show some claims at least. Okay, so this is what I'm going to do, and I'm not going to very carefully provide you all the details now. You can look at it when the slides are given to you. But essentially, I'm going to use this Taylor series with remainder and write down, this is for the forward difference. I'm going to at least show it to you for the forward difference. You can do it for the backward difference. Sorry, this is the backward difference. You can do it for forward and central difference on your own. Okay. So using the Taylor series, I can sort of put things together and get this to be the error in the forward difference. Okay. So there is this true value, and then this is the forward. So backward difference, I think this is the backward difference, this is the true value, and then I compute its error, and it's a small, simple analysis thought process. It's straight, this is all it is, but you'll have to argue that if I take the absolute value here, it's going to be sort of bounded by this function. I take some absolute value of this function and then take the maximum of that absolute value, and I just denote that as u double this, the norm of this u double dash. Okay. Again, the intent here is for completeness. If you have not fully followed it, don't worry about it. Take a look later and ask me or email me later if you feel like it. Okay. But I can use this to therefore generalize that the forward and backward differences go to 0 as O of delta x. So they linearly go to 0. In the limit that delta x goes to 0, this error goes to 0. For the centered difference, this error goes faster to 0. It goes as O of delta x squared. This is the big O notation. So this is in some sense more accurate than the forward and central differences. This is where I use the xj plus 1 and xj minus 1 to compute the derivative at xj. Okay. So, and these are for the first derivatives. I can sort of combine the first derivative operators, difference operators, and compute the second derivative as well. It comes kind of like the same Taylor series idea works through. I'll have to write u of xj minus delta x. I get with some minus signs. I add the two together and or subtract, do some algebraic operations. I would get the second derivative operator as well. Okay, so this is the approximation of the second derivative. And that approximation is indeed an approximation. In the limit, it goes to 0. Okay. And then there are some mathematical constants. We can safely ignore them. We can believe that these constants will be finite in all applications.
Okay, quick question. Why do
Yes.
we do first, as in the forward one first and then the backward one? Is there some order to it, or is it like either way you can?
So I sort of foresaw this question. And maybe I forgot to write it. It turns out if you did plus or minus or plus, it doesn't matter. You will get the same second order
Okay,
differentiation.
if we do central twice, then
Yeah,
still we'll
then
get
you'll
it.
get, no, then you'll get a different second order approximation. And it'll in fact be more accurate than delta x squared. It'll be delta x to the power 4, I think. Yeah.
Okay.
If you do centered twice for this, you'll get, and that's the trade-off. Okay, again, some things I didn't touch upon. There is a famous paper by Max Wardetsky called, it's Wardetsky with the guy who used to be at New York University, now moved to Toronto. There's the paper and has Saurabh Mathur is one of the authors. It says there's no free lunch with discrete approximations or discretizations of Laplacian. The problem with taking two-centered difference is that I'll end up taking many more to compute the second derivative at xj. I'll need xj minus 1, xj minus 2, xj plus 1, xj plus 2. Okay, I'll need much more data to compute it, and that's the cost. There's always a cost in scientific computing, numerical analysis. It's the cost is accuracy versus how much computations you can do. So with more data, you can do more computations and you'll get more precise answer, but the flops will increase as well. And these days, flops themselves are not important. It's really a memory issue, I think, more for like lots of computations. Flops are for free, they would say. Anyways, to recap, this answer to your question is, this is the same as del partial minus partial plus, and with partial hat, you'll get a more accurate second order derivative approximation. Okay, so we shall now use this difference quotients to discretize the Laplacian. Okay. Again, I think we are doing okay with time. So let me know if I'm too fast or if I'm too slow. If you want me to speed up, that's okay as well. If you want me to go slower, that's just let me know. And I'm not monitoring the chat. So if you said something there, I would have missed it. Okay, looks like no one said anything there. Okay, so we are now entering into the territory of numerically solving a PDE. Okay. Okay, so this is my Laplacian in one dimension, and I'm going to use this approximation, partial plus followed by partial minus. And I can write that down. If I did the algebra, this is what it'll come out to. And it's, if you're familiar with it, you know, it's the standard second order approximation stencil, as it's called, 1 minus 2 1. Okay, so this is my Laplacian in 1D. Okay, I did write it down, like maybe I did foresee it. So plus minus is the same as minus plus. Okay. So the Poisson problem is the following. It's Laplace is u equals f. So I know how to discretize the Laplace. The Laplace is this d square u by dx square. I use this approximation. It's a provably correct approximation, which means it in the limit, it will give me the correct true solution. So I can use this without worry. I've already exhibited the proof of it. That's what you need to worry about in math. How do I do things provably correctly? Yeah. In computational math or applied math, at least. Yeah. Okay. So I have this Poisson problem. I have this approximation for the second derivative. For f, I'm going to approximate it as, call it fj. Okay. I've put it down later. Fj is simply f evaluated at xj. So I'm given a right-hand side function. Remember, I was given this right-hand side function and I was asked to find what u is. So I can therefore use this to compute fj, which is simply at the grid points I evaluate f. Okay, that's my fj. Okay, and then there are these boundary conditions. So this is given, again, this is this is the problem that's been in the back of my mind all throughout. Poisson equation with this Dirichlet boundary conditions. Okay, so I'm given some Dirichlet boundary condition at both the left and right hand side points, and I use it to set up my u0 and un, which, like I said, with some of these methods, I wouldn't be able to compute it. Even here, there is no, at the rightmost point, there's no uj plus 1. At the leftmost point, there's no uj minus 1, but I don't have to worry about it because I'm given the value anyways there. Okay. So this, if I throw this in here and I use this fj, I can write this whole thing up as a matrix problem. It becomes, so it's going to essentially be, I could have written it down, but equals fj here. So I have uj minus 1 minus 2 uj plus 1 divided by delta x square equals fj. And that's true for all the interior grid points. And I can assemble it into this matrix system where the vector of the vector u is the vector of unknown values at the grid points. My right hand side consists of the evaluation of given function on the grid points and the boundary conditions, and this matrix would pop up. Okay, notice this is going to be essentially a tri-diagonal banded matrix. It's minus 1 2 minus 1 minus 1 2 minus 1 and so on until this minus 1 2 minus 1 hits this end. But the first and the last rows are just 1 0 0 0 and 0 0 1, because what we are saying is we are setting this times this equals u of x0. So essentially we are saying u0 is u of x0 and un is u of xn. Okay, so I hope this is convincing enough that this leads to this linear system where the matrix I'm going to call it A, and this right hand side vector I'm calling it B, and my unknown solution is U. Okay.
Is this like we are presuming numerical stability, as in while meaning with that stencil thing?
Okay, by numerical stability, what do you mean? Because we have shown in the proof, we have shown it's consistent. The discretization is consistent. But I don't, because stability means many things to me, and I want to try and understand. Is it stability of the PDE that you're talking about? Or?
No. Of the series of the function itself, the function and the PD, as in eventually the approximation should basically converge to the same values.
Right.
So,
but that aspect for the finite difference scheme is more or less just this proposition. There's more to it. I understand. This is just consistency, and you're on the right track. You need to show that this is this is consistency. You need to show that the discrete solution is stable. That's right. But I am not going down that route as well. It'll be too much work. But I'm going to use this proxy instead of running it through that argument. I'm just going to argue that this matrix is non-singular, which is equivalent to saying that the discrete problem is stable. Okay, the smooth problem is already stable. You have to be given a smooth problem that is stable. We're not interested in solving unstable smooth problems. So as an input, you're already assumed to be given a smooth problem for which there is a unique solution even. Okay. And the question is, like you're asking, it's a great question, which is that how do you know that I've just shown that the discretizations are convergent, but now putting it all together, I don't know if this will even give me any meaningful discrete solution, right? Which is the question of stability of the discrete problem.